Okay, so let me begin with the material for today's class. We're really moving on to a completely new topic and a completely new um, viewpoint in today's class, or at least beginning in today's class. So in the past classes, we've done a couple of things. We've worked on describing motion. We talked about, displacement, velocity, acceleration. And we worked on explaining motion. We talked about forces influencing motion and Newton's laws describing how forces influence motion. And we looked at lots of examples, right? We looked at examples of bodies falling under gravity, projectiles moving under gravity. We've looked at problems with inclines. We've looked at problems with pulleys and much, much more. So beginning in today's class and continuing over the next classes up until test 2, we're going to discover that hidden beneath these sort of changes in motion, or these influences of motion by forces, by the action of forces, are some very important conserved quantities. And you know their names, I'm sure. One of these conserved quantities is energy, and another one of these conserved quantities is momentum. And they give us a new way of understanding motion. They give us a deeper understanding of movement. And so the next classes are all about energy, momentum. Today's class, we're going to begin our work on energy and momentum by introducing the notion, or introducing the idea, that forces do work. And we're going to talk about work today. And then we're going to say a few words about different classifications of forces, what we call conservative forces, non-conservative forces. And then we'll finally discuss what we call the work-energy relationship. So the notion of work, the concept of conservative, non-conservative forces, and the work-energy relation are the content of today's class. And that content will lead into our future classes where we discuss energy and where we discuss momentum. Okay, so sometimes Lady Gaga comes to class. She hasn't been to class for a while, I noticed. But she comes to class when there's big new ideas, big new concepts being introduced. And it's important that our investigation of energy is a big new concept. It's going to allow for a much deeper understanding of motion, of matter. And it actually revolutionized all of science, from physics through chemistry to biology. I'm not going to say too much about energy in this class. We're really going to be talking about work in this class. But let me just give you one way of thinking about energy, or one analogy to energy. Actually, Lady Gaga has given us this analogy to energy and way of thinking about energy. And it's that energy resembles money. So in our society, right, money kind of flows around from owner to owner, person to person, and from form to form, right? I might have money on my credit card, or I might have money in cash. But money we don't create and destroy money. Energy is similar, right? Energy also flows around from owner to owner. It flows around from form to form, but energy isn't created or destroyed. And so in that way, how money operates in our society and how energy operates in science are really rather similar. Now, they're not exactly the same, right? You can actually create and destroy money. I could burn the money in my wallet. The Federal Reserve can print new money. But mostly in society, money just moves around, flows around. Energy, on the other hand, as far as we know, you can never create or destroy energy. It only can move around from one owner to another owner, one form to another form. Okay, so that was just the big picture. Today's class is really going to begin with a simple machine. A story begins with a simple machine. It's a lever, and it introduces us to the concept of work. Humans didn't even, Homo sapiens didn't even invent this machine, okay? Before Homo sapiens, this machine, the lever, was invented. And so it's really the most ancient machine. And this most ancient machine will lead us to the idea or the notion or the concept of work. Okay, so as I said, levers were invented a long, long time ago, I guess in a land that was far, far away, and not even by Homo sapiens. And here's a picture of a lever. And in this picture, I am showing sort of the components of the lever. So let me get my pen working if I can. So it'll only take me 20 minutes, I guess. So in, I don't know what this color is, aquamarine maybe. Here is the lever, this long bar here from left to right. And there's a pivot point down here. So here's the little pivot point. And on the lever, we've got one large mass over here on the right. No, that's the left. And we've got one smaller mass over here on the right. And with this lever, we could use the small mass to lift the large mass. And that's kind of how we use levers. So let me talk about how levers work and how we use levers and what levers are useful for and what physics is inside, hidden inside levers. Okay, so a key thing about a lever is that you can turn a small force or a smaller force into a larger force. Now, that seems almost like magic, that you could make a small force turn into a large force with a lever. But it comes at a price, it comes at a cost. And so let me just describe how we turn a small force into a large force and how it comes at a cost. Okay, so here's my lever again. Here's the pivot. Oh, everything's gone out of control, sorry. Here's my lever again. Here's the pivot point. And what I'm going to do on this slide is use this smaller mass that's over here on the right to lift this larger mass that's over here on the left. And I can lift the larger mass with the smaller mass because I place the pivot of the lever close to the larger mass, further away from the smaller mass. So when you place the smaller mass on the incline, on the lever, it creates a force on the lever. That force is just the weight of the smaller mass. And that's a downwards force on the right-hand end of the lever. So this is the force that we're putting into the machine. And then that creates, from the lever exerts an upwards force on the large mass at the opposite end of the lever. And that large force is what lifts up the mass with the lever. And the amount of force that we need to lift the mass is also the weight of the larger mass that's over here on the left-hand side. So that's the way in which a lever can turn a small force into a large force. We put a small force into the lever by applying this small mass over here, and the force we put in is its weight. And we get a large force out of the lever. That's this large force over here on the left that's lifting the larger mass, the larger weight. So that's turning the small force into a big force. But there was a cost with that. It wasn't just magic. This mass on the left has to move the lever a large distance to raise the larger mass just a small distance. And so that's what I'm trying to picture here and here, is that whilst we did put in a small force and did get out a large force, we had to apply that force over a large distance into the machine to get out a large force applied over a small distance from the machine. So that's the cost, that's the price, that's where there's no free lunch. Okay, let me go on to the next slide. So that gives you an idea of the utility of the lever. So not only can you use a lever to turn a small force into a large force, but you can use a lever to turn a small displacement, small movement, into a large displacement, large movement. And that's what's shown in this slide here. So now I've got the lever arm again in aquamarine, or whatever this color is. I've got the pivot point now. Oh, keep doing this, sorry. I got the pivot point over here on the right-hand side rather than the left-hand side. And I'm going to use the large mass to put in a force to the lever and get out a force, a smaller force over here on the left-hand side. So when I apply this large mass to the right-hand side, apply it to the lever, it moves the lever by a small amount on the right-hand side. That's this displacement here. But that creates, because of the location of the pivot point, a much larger displacement over here on the left-hand side. And so that's how you can use a lever, not only to turn a small force into a large force, you can use it to turn a small displacement into a large displacement. We put a small displacement in and we got a large displacement out. But again, there's a cost of doing that. The cost is that small displacement has to be exerted by a large force. We had to put the large mass on the right-hand side. And we would only get out a small force from the machine over here on the left-hand side. We get a large displacement, but the force that can be applied is smaller. So again, you can turn a large displacement, a small displacement into a large displacement with a lever with this machine, but there is a cost, there is a price that small displacement has to be exerted with a large force, and the large displacement you get out corresponds only to a small force. Okay, so that's kind of nice, how you could use a lever as a machine to make small forces into large forces, or make small displacements into large displacements, understanding that there is a price, that there is a cost to either of those ways of using a lever, ways of using the machine. It was Archimedes. This is Archimedes upstairs here in the top left-hand corner. I hope it's Archimedes. I guess question mark. I think it was. Who actually put those notions of how to use a lever to make big forces from small forces, or big displacements from small displacements, into a law of levers. So he came up with the law of levers. And the law of levers is basically that the product of the force that you put in to the lever and the distance you apply that force. So that's on this right-hand side in this picture. We're putting in a force and we're applying that force over some distance, is equal to the product of the force that you get out of the lever and the displacement that you get out of the lever. So in this particular example, I put in a small force and I put in a large displacement. I got out a large force and a small displacement. But the law of levers, Archimedes' law of levers, says that the product of force times displacement in equals the product of force times displacement out. And you can see how that might be the case, right? Small force times large displacement equals small displacement times large force for this example. We call that product of force times displacement. We call that the work done. And so that's the work done on the machine. So the work that we put into the machine is the force times displacement over here on the right-hand side. And then over here on the left-hand side, that product of force times displacement, that's the work we get out of the machine on the left-hand side. And so we now think of levers not as just in terms of the forces we put in and get out and the displacements we put in and get out, but now we're thinking of this more abstract quantity, the work that we're putting in to the lever, force times displacement, and the work that we get out of the lever, force times displacement. And the key thing is, it's written down here, that the work in to the machine equals the work out of the machine. The work into the lever is the work out of the lever. And so that explains, how you can make big forces from small forces or big displacements from small displacements at the cost of, or the price of, if you make a big force from a small force, you've got to put in a big displacement. If you make a big displacement from a small displacement, you've got to put in a big force. It describes all of that. It's very nice. I like it. 2,000 years ago. That's quite good. Okay. Now, let me make a remark about this statement that work is force times displacement. Because I want to be careful about this statement that work is force times displacement. The thing is that, if you remember, forces are vectors. They have both size and direction. Displacement is a vector. It has both size and direction. So when I say that the work is the force times the displacement, I'm being a bit loose with, what I mean by that. I'm being a bit vague with what I mean by that right now, because force is a vector, displacement is a vector. How do I multiply these two vectors together? I got away with it in the lever. I was lucky with the lever because the force and the displacement that you put in were in the same direction. The force and the displacement that I got out were in the same direction. And so in the lever, you only have to multiply the size of the force times the size of the displacement that goes in, and the size of the force and the size of the displacement that you get out. But in general, the work done by a force over some displacement might not involve the force and the displacement being parallel to one another. So I want to say, how do we deal with that? How do we handle that? Well, the next slide. The next slide is physics definition of work done by action of a force. So if you look at the equation in this slide, W is, I knew I was going to do that. I knew I was going to do it, but I couldn't quite stop myself in time. Okay, so this W is the work done. That's what we're going to calculate from the force and the displacement. This is the size of the force. I put the vertical lines either side of the F for force to indicate that's the size of the force. This is the size of the displacement, delta x. put the vertical lines again to indicate this is just the magnitude of that displacement. And then this cosine theta. That theta, look downstairs at the picture. That theta is the angle between the force that's exerted, the red arrow, and the displacement that occurs, that's the blue arrow. So the relative direction of the force and the displacement, that enters the calculation of the work done through this angle here, through the cosine of this angle here. So if the force and the displacement were parallel to one another, which was the case of the lever, then that's the cosine of 0 degrees. And the cosine of 0 degrees, I'm sure you remember, is 1. So then you do just get force times displacement, the magnitude of the force times the magnitude of the displacement. But in general, that's not true. There's a couple of interesting cases here. Look, supposing there was 90 degrees between the force and the displacement. Well, the cosine of 90 degrees, if I remember my cosine of 90 degrees, that's actually 0. So you could have a situation where a force is acting, where there is a displacement. Those are two ingredients in work being done. But because the force was at right angles, 90 degrees to displacement, there's no work done by that force. So this multiplication of these two vectors upstairs here, I'll just make a remark. It's called the scalar product of two vectors. And it doesn't yield a vector, it yields a scalar quantity. Work done, or the work, is a scalar quantity. It itself just has a size, although it's made of two vectors. And that size we measure in, well, the units of force are newtons, the units of displacement are meters, so we could measure it in Newton meters, but it's so important. We give it the name joules, and we give it the symbol J. And so that's our definition. That's our definition of work. Okay, let me make some comments on work done by forces when forces act. So just stress this one, I already said it, but work is a scalar quantity. It can be positive, so you can do positive work. It can be negative. You can do negative work, so that's important. And it can be 0. You can have forces and displacement, but it could be that the work done is 0. Work doesn't have a direction. It doesn't have an orientation. Work is always done by something on something. So, you know, when I hammer in a nail, God forbid I hammer in a nail, but when I hammer in a nail, the hammer is doing work on the nail. The hammer is exerting a force on the nail, and the hammer is doing work on the nail. So work is done by something on something. We have to be a little careful about, we use work in everyday language, and we use work in physics language. And the physics language and the everyday language are a bit different. So as an example, right, thinking. I'm sitting here and I'm just thinking. Well, everyday language, I'm doing some work, really hard work. I'm thinking. Physics language, I'm not doing any work. I'm not moving. I'm not exerting forces. So no work's done. So physics work always involves forces and displacement. Everyday work can be thinking work or other types of work, and may or may not involve work being done, physics work being done. Sometimes we'll talk about the work done that's by a specific force. So we might talk about the work that's done by gravity, or we might talk about the work that's done by friction, or we might talk about the work that's done by the normal force. Other times we'll talk about what we call network. That's done by net forces. So if you have an object, an apple, and number of forces act on that object, act on that apple. Those individual forces will do some work, but the total work that's done is the net, what we call the net work that's done on the apple. And it's related to the total force, the net force that's acting on the apple. So the net force acting on the apple does net work on the apple. Okay, so now I want to turn to some examples of calculating, mostly calculating work done. I want to show you a little demo, a couple of little demos, I think, first, before we do that. Okay, so I hope you can see, this is back in the chemistry physics building in the physics lecture room, where we would have been. It's very sad. But I'm going to show you a demonstration of the lever. And now we have this deeper understanding of the lever. You know, we can put in big force, little forces and get out big forces at the cost of big displacements in and small displacements out. And we can understand it in terms of the work into the machine being equal to the work out of the machine. So let me show you this video. Basically, what I'm going to do is show you where I put a small force into the lever and get a large force out of the lever, meaning I put a small weight on the lever and lift a large weight with the lever, but the cost will be a large displacement. And here it goes. I put that 16 pounds, I could barely lift it over there on the left-hand side. Now there's 8 pounds on the right-hand side. And with 8 pounds, I lifted the 16 pounds. So it's a small force in and a big force out. That's real magic, but it's not really magic because I had to put a large displacement in for the 8 pound weight to lift the 16 pound weight, a small displacement. So the displacement of the 16 pound weight was much smaller. The displacement of the 8 pound weight was much larger. Now I put a large force in and get a small force out, but look, the large force in, I only had to displace it a little bit to displace the smaller mass a lot. So that's where I get a large displacement out from putting a small displacement in at the cost of the force I put in being big to get a small force out. And so that's really, that's the lever and how we understand it in terms of work in equals work out. I'll show you one more demo. So these are pulley systems, which are also simple machines. And in the first case, I'm going to show you, with the pulley system, I'm going to move one mass with another by moving another mass where the two masses are the same. And then in the second case, I'm going to show you where I move one mass by moving another mass where the two masses are different, where the one I move is actually heavy and the one I touch is actually light. So let's see how that works. And it's an example similar to the lever. So those two masses are equal. I put a small force in and I get a small force out. The small force I put in pulls down one mass and the small force I get out lifts up the other mass. And so I'm getting the same force out that I put in, and I'm getting the same displacement out that I put in. Now I'm going to go over to the machine on the right, and you see I'm putting in a small force by moving the small mass and getting out a large force that moves the large mass. And then here I put in a large force that, well, I'm getting ahead of myself. When I put in the small force to move the large mass, the motion of the large mass, if you noticed, was small, much smaller than the motion of the small mass. So again, the work in to that machine was equal to the work out of that machine. I can make a bigger force, but the cost is I need to put in a bigger displacement. Or you could make a bigger displacement, but the cost would be you'd have to make a smaller displacement. I see in chat, let me go to the chat quickly here. Okay, can gravity do work? Well, I'm going to talk about that, but yes, gravity can do work. Does that mean the work done by gravity is negative? The work done by gravity, we can see, can be negative and can be positive. Um, does gravity do work on objects if objects move horizontally? Well, we'll take a look at that. That's a good question. Okay, so now I'm going to go back and share my, so those were great questions, actually. Let me share my slides again. And those questions, you like your mind reading me, you're anticipating me just a little too much, a little too uncomfortable there, because we're going to talk about exactly those things now. And I've got to, every time I share screens, I lose the chat, so I've got to get that back. Okay, so first, so I'm going to look at examples of calculating work now, but the first one is just not calculating it, but just whether it's zero or not zero. So in this slide here, you know, this is me at home, me the handyman, lifting up a floorboard with a crowbar. And when you lift the floorboard with the crowbar, right, the crowbar is exerting a force kind of upwards on the floorboard. The motion of the floorboard is upwards. And because the force and the motion are in the same direction, the cosine of the angle between them, that's going to be 0 degrees in this picture. That means that's an example of positive work being done on the floorboard. So that crowbar is doing positive work on the floorboard. Here is an example of zero work being done. Now, this is an old picture from my school book where we had a tug of war. I don't know if you can see the rope, but the rope is here. So this was Team A, I remember it well, and this was Team B. And actually, I was too nervous to join in, so I'm over here, standing watching. And so the tug of war is going on, but actually, neither side was winning. They're pulling hard. Team A's pulling hard towards the left. Team B's pulling hard towards the right, but they just weren't moving. So this is a situation where, you know, the tension force on Team B over here, well, that's a force that's acting towards Team A, but there's no displacement of Team B. And so there's no work being done on Team B. And likewise, there's a force on Team A, I didn't draw it, over towards the right, tension force, but Team A isn't moving. And so because they're not moving, because they're not displaced, there's no work done in that situation. So an example where in everyday language, or I'm standing there watching and I'm saying, Team A and Team B are really working hard. But if I knew any physics when I was 8 years old, I would have said, well, actually in physics, Team A and Team B, they're not having any work done on them. They're not doing work on each other because they're not moving. So that's an example, again, of the physics definition of work done. Okay, I got a quiz here. Okay, so that's a question. If I go to the next slide, I've got the question written down, I think. That's a question about a particular force, the gravitational force, doing work on this object. So there is a non-zero gravitational force, of course, on that sleigh. The Earth is pulling the sleigh downwards. There is a displacement of the sleigh. The sleigh moves from the left to the right, but the work of gravity on the sleigh is zero. It's not because gravity is zero, it's not because the displacement's zero, it's because of the relative orientation of the gravitational force and the sleigh's displacement. They're at 90 degrees to one another. They're at right angles to one another. And the cosine, mathematically, the cosine of 90 degrees, that's 0. And forces that act at 90 degrees to the motion do no work. And we'll come back time and time again, actually, to the fact that forces that act perpendicular to the motion at right angles, 90 degrees to the motion, actually do no work. Okay, now I want to do calculation. Kind of like calculations sometimes, and I feel like one coming on right now. So in this example, we're going to load a crate into a truck. And actually, I've asked Bill and Ben to load two identical crates, into two identical trucks. And it's pictured on the left and pictured on the right. And I got to get my annotation back. That's the other thing I always lose. So over here on the left-hand side, this is Bill. He's going to load the crate into the truck. And what Bill's going to do is going to lift it just straight vertically upwards and put it on the truck bed. And then over here on the right, this is what Ben is going to do. Ben is going to get an incline or a ramp, 30-degree incline, 30-degree ramp. Here it is. And slide the crate up the truck. Slide the crate up the ramp. And so that's Bill's way is the straight lift, and Ben's using the ramp to get the crate on the truck. And we're going to compare them. And to compare them quantitatively, we're going to use the fact that the mass of the crate is 20 kilograms. The height of the truck bed is 1.2 meters. The incline used by Ben is 30 degrees, and we're going to not worry about, we're going to ignore friction on it. We're going to imagine it's frictionless incline. Okay, so let's do the calculation then. Get rid of that. Go to next slide, maybe. Maybe not. Okay, we're going to do Bill's work done. How much work does Bill do on the crate? So here's a picture of Bill's force that he exerts on the crate to lift it up. And then we're going to do the calculation of Bill's work done on the crate. So, when I wanted to picture Bill's force that he needs to exert to lift the crate, what I'm picturing is, well, look, the crate is pulled down by the gravitational force. And it was a 20 kilogram crate, so it's 196 Newton gravitational force or weight of the crate. Now, to lift the crate up gradually, Bill has to counteract that force with the force that he applies. And so he needs to apply a force that will counteract the weight of gravity. And so that will be 196 newtons or so, but upwards instead of downwards. And with those two forces, right, the net force on the crate will be 0, and he can slowly move that crate upwards, glide it upwards. And so that's how he gets it on the bed of the crate. And so that's the kind of the force diagram for Bill's lift of the 20 kilogram crate. Now we want to calculate the work that's done by Bill. And I've got to go to the next part of the slide. Here it is. So I'm going to use our equation for the work done. So that's our starting point as that general formula for work done. Here we are. Size of the force times size of the displacement times the cosine of the angle between those two vectors. Well, look, the force is 196 Newton, as Bill's exerting. The distance he exerts it over is the height of the truck bed. It's 1.2 meters. And the cosine is the cosine of 0 degrees because the force and the displacement here, they're both upwards. They're in the same direction. And if you do that calculation, this comes out to be 235 joules of work plus positive 235 joules of work. And so that's Bill's work done. Now let me do, who was Ben was the other one. So I need to go on to the next slide, and we're going to do Ben's work. So here's a picture of Ben's situation. Remember, Ben is using the 30-degree incline over here and sliding the crate up the frictionless incline. Now, the advantage, you know, Ben's pretty smart, at least Ben potentially smarter than Bill. So Ben is thinking that, well, if I use the incline, I don't have to apply a force that's the full force of weight of the crate to lift it up. I can just overcome the fraction of the gravitational force that acts down the incline. So that was his idea. So I've kind of drawn a force diagram of this situation. So we got the weight of the crate that's acting down the incline. Let me get my pen going here. That's over here on the left. So the portion of gravity that acts down an incline, if you remember, is the weight times the sine of the angle of the incline. So it's W sine 30 degrees in this situation. If you calculate it, it comes out to be 98 newtons. Remember the full weight, that was 196 newtons. So it's half of that weight. And that means that Ben himself has to only exert that 98 newtons in the opposite direction to gradually slide the crate up the incline. So here's Ben's force. It's also W sine 30 degrees. It's also 98 newtons. So Ben is using half the force that Bill used. However, the cost is that Ben has to push the crate the full length of the incline rather than just the height of the truck bed. So Ben needs to push the crate this total length of the incline here, not the 1.2 meters was the height of the truck bed. So we need to know the distance, the length of the ramp that Ben is pushing the crate up. And that's just a little bit of trigonometry, right? We know that the opposite side of this triangle involving the ramp is 1.2 meters. We know that the ramp itself is the hypotenuse of that triangle. So based on sine 30 degrees being opposite over hypotenuse, the length of the hypotenuse here is the length of the opposite, the 1.2 meters, divided by sine of 30 degrees. And that comes out to be 2.4 meters. And so Ben is using a smaller force, but is exerting it over a larger distance. Okay. So now we can do the calculation of the work done. So our starting point, oh, God. Our starting point is, that's the wrong one. Here we are. Our starting point is, again, our definition of work done in physics. It's this little equation here. It's the size of the force times the size of the displacement times the cosine of the angle between those two vectors. So the size of the force is now just 98 newtons. The displacement, though, is larger, 2.4 meters. And the angle between them, you've got to be careful here. It's not the angle of the incline. It's the angle between the displacement, which is up the ramp, and the force that Ben exerts. That's also up the ramp. So the angle between Ben's force and the displacement is 0 degrees. And so it's the cosine of 0 degrees. And so that's this one here. And then if you multiply those three quantities, you discover that Ben does 235 joules of work. So that's the calculation for Ben. Now, I'm sure you've spotted the interesting thing here. If I can get to the next slide. yeah, that the work done by Bill lifting the crate straight up, that was 235 joules. The work done by Ben in sliding the crate up the ramp, that was also 235 joules. Intriguingly, they did the same work in lifting the crate up onto the truck. They both did 235 joules of work in lifting the crate up onto the truck. They used different forces. They had different displacements of the crate, but they did the same work. And this is a big clue. It's a big clue to a deeper understanding, a fuller understanding in terms of energy that we're going to return to later on. But for now, it's just an example of calculating the work done by individual forces, Bill's force, Ben's force, when an object is displaced, moved by those forces. Okay. Let's look at another calculation here, another example here. So in this calculation, I'm going to imagine a crate that's sliding down an incline. It's this 1.5 kilogram crate, and it's sliding down this 20-degree incline. So here's the mass of the crate, here's the incline, and it's going to slide down 0.6 meters. And I didn't put it on the figure, but we're told that there is friction on this incline, and the coefficient of friction is 0.12. So those are the parameters of the problem. And this is really an important diagram to picture the problem. And we're asked to figure out the work done by a number of different forces. What's the work done by gravity on the incline? What's the work done by the normal force of the incline on the block? And what's the work done by the frictional force of the incline on the block? And what's the net work done, the total work that's done by all of those forces doing their works? So we're going to answer all of those questions. And so let me move on, clear this, find my way to the next slide. Here we are. So the first thing I did was actually, what we got used to doing before test one, and that we, was to me one of the more enjoyable things. It's drawing the diagrams of the forces that are acting and that potentially affect the motion or influence the motion. So that's what I'm drawing on this figure. So again, here in the middle of the figure is the mass on the incline, or the block on the incline. And I want to draw the forces that are acting on that mass. And I've also indicated the directions of those forces. And I'll say something about that after we've gone through the sizes of these forces. So one force obviously is gravity, or the weight. And I've indicated that by this magenta downwards arrow here. So that's Earth pulling the crate down. And the weight of the crate is the mass of the crate times the acceleration of gravity. And it was a 1.5 kilogram crate. So it's a 14.7 Newton weight crate. And so we know the gravitational force's size, we know its direction here. The normal force. The normal force, if you remember, is stopping the crate from smashing through the incline. It's balancing, it doesn't balance the full force of gravity, but it balances that component of gravity. I'm trying to draw it here. That is perpendicular to the incline. So that's Fg cosine 20 degrees, or the weight cosine 20 degrees. That's gravity's pull into the incline, and the normal force is balancing that. So the normal force here will be the 14.7 Newton gravitational force times the cosine of 20 degrees. And if you calculate that, you get 13.8 newtons. So that's the normal force. And I've indicated its direction, right? Its direction is perpendicular to the incline. The normal means perpendicular. And so it's at right angles to the incline. Finally, the other force acting here is friction. There is friction on the incline. If you're sliding down the incline, the frictional force will oppose the slide down the incline. The frictional force, if you remember, here it is, F with a subscript F to indicate frictional force, is equal to the coefficient of friction times the normal force. That's our rule for the frictional force. Since we know the normal force is 13.8 newtons, all we got to do is multiply it by the coefficient of friction, which was, I think, 0.14. And I did that, and I got a 1.7 Newton frictional force. And again, I've indicated this red arrow here is meant to indicate the frictional force, including its direction, which is opposite the direction of motion. And so this was an important figure, important diagram. It shows me all the forces that are acting on the crate and the directions of those forces and the magnitudes. I know the magnitudes of all those forces. Now we can quickly figure the work done. Now most of our work in some sense is done. If I can get to the next slide, that is. Okay, so I'm getting to the next slide. I've got to clear up all this junk, and here we are. So I've just reproduced the diagram actually here from the last slide. And now I'm going to do the calculation. So let's go through the calculation of the work done by gravity. I call it WG, the work done by normal force, WN, the work done by friction force, WF here, and the net work done that's done by all of these forces. Okay, here's gravity. So for gravity, what did I do? That's a good question. Let me figure it out, get the pen going. Here's gravity, and I'm going to multiply the size of the gravitational force by the size of the displacement by the angle between these two, this force and this displacement. That's this 70 degrees here. So you have to be careful. That's not the angle of the incline. That's the angle between the action of the gravitational force and the displacement of the crate. So that's the 70, cosine of 70 degrees here. And I put in all the numbers, right? I know all the numbers. I got 3 joules plus 3 joules of work is done by gravity on the crate. So that's where gravity is, you know, in the quiz example, the object moved horizontally and gravity did no work. On the incline example, the crate is moving downwards and gravity is doing some positive work. Okay, now we've got to do the next one, which is the normal force. And so here I'm doing the normal force, so Wn. Again, I'm multiplying the size of the normal force by the displacement of the crate by the cosine of the angle between them. So here's the size of the normal force, here's the displacement, we know those things, and then here is the cosine of the angle between them. But look, they're at 90 degrees to one another. Remember, this is a special angle for work done. And so cosine of 90 degrees is 0. And so this is one of these famous examples where you got a force, you got a displacement, but that force does no work because the normal force here is perpendicular to the motion. And so that's pretty interesting, I think. Okay, next one is the the work done by friction. So here's the work done by friction. I hung the little subscript F on it. Again, I'm getting tired of saying this, but this is the size of the force, the frictional force here, the size of the displacement times the cosine of the angle between them. Again, got to be careful. That's not the angle of the incline. The motion is down the incline. The frictional force opposes that, it's up the incline. The angle between the motion and the frictional force, it's 180 degrees. And so we got to multiply the frictional force times the displacement times the cosine of 180 degrees. And you might remember, I remember, cosine of 180 degrees is the famous -1. And so we end up that the work done by the frictional force is not zero. The friction between the incline and the crate is doing some work, and it's negative 1.0 joules. It's a negative amount of work that's done on the crate. The gravitational force was doing positive work on the crate. So that's interesting. Okay, we got one more to go. We got to calculate upstairs here the net work that's done. And that is simple when you know the work done by the individual forces. So let me do that, if I can. Here it is. So here I'm calculating the net work that's done. And to figure that, all I have to do is add these three numbers that correspond to the work done by gravity, work done by normal force, work done by frictional force. That's 3 joules plus 0 joules plus -1 joules. The end result is that 2 joules of net work is done on the crate. And that's the answer to that part of the problem. Okay. Let's move on. Somehow that one exhausted me. And we're going to clear all this. And I want to mention, it's quick, conservative and non-conservative forces. What's the difference between conservative and non-conservative forces? What's the distinction between conservative and non-conservative forces? Okay, so gravity is the classic example of a conservative force. So anytime somebody would say to me in the street, right, what's a conservative force? I would always reply gravity. It's a classic example. And the key feature of a conservative force is that if you move an object from one location to another location, and then move it back from that new location back to the original location, and you add up the work that's done on those two stages, moving to the new location, moving back to the old location, the total work done by that force is 0 if it's a conservative force. And so I've tried to show that in this picture here. Look, I've taken an apple near the Earth's surface, and firstly, what did I do? I lifted up the apple, and so that's pictured over there on the left-hand side. Here I'm lifting up the apple to a greater height and putting it back in the tree, say. And when I do that, my displacement of the apple is upwards, my gravitational force is downwards. That's negative work done because the direction of the force and the displacement are opposite one another. So this is negative work. Then I take the apple back down from the tree and put it back on the ground. So in that case, the work the displacement is now downwards instead of upwards, but gravitational force is still acting downwards. And so this time the work done by gravity, because the force of gravity and the displacement are in the same direction, that's positive work. And if you actually were to calculate the number of joules of work that's done on the way up and the number of joules of the work that's done on the way down, and add those joules of work together, you would discover that no net work has been done if the apple returns to the original location. And that's a conservative force. That makes gravity a conservative force. You might wonder, well, perhaps all forces are conservative forces. But if they were, we wouldn't use that word, of course. Friction, if I get to the next slide in the next 20 minutes, friction is the classic example of a non-conservative force. So the thing about a non-conservative force is if you move an object from one location to another location and then move it back to the original location, a non-conservative force will do some net work. For the conservative force, if we moved it from one location to another location and moved it back again, there was no net work done overall. But for a non-conservative force, there is a network that's done overall. And you can see how it works for friction. Because remember that frictional forces always oppose the motion. Frictional forces always oppose the movement. So in this example, I'm going to take the apple again, and it's on the left-hand side of the table. I'm going to slide it across to the right-hand side of the table and then slide it back to the left-hand side of the table, to the original position. So here is where I'm first sliding the apple to the right. And because of the friction, right, as I move the apple to the right, that's the red arrow, there's a frictional force to the left. So the frictional force is doing negative work because it's opposite the direction of motion. Then I slide the apple back across the table. The apple is now traveling, displaced in the opposite direction, but the frictional force still opposes the motion. So it's now also reversed. So still, because both the displacement and the frictional force have reversed their direction, the friction and displacement are opposite one another. And so in this case, negative work is done on the way back also. And so when I add up these two amounts of work, they're no longer zero. They're not zero for the frictional force. And so, again, if I was walking down the street and, I don't know, President Capilouto asked me, you know, give me an example of a non-conservative force, I would say friction. I'd always say friction. It's the classic example of a non-conservative force, that if you slide something from one place to another and slide it back, the frictional force will do net work. Okay. Last topic, and I got how many minutes? Can't see with my glasses. I've got 9 minutes. Okay. Want to introduce the final topic for today, which is a link between work that we've been discussing and a new quantity, which is energy, that we will be discussing. And it's called the work-energy relationship, because it's a relationship between work and energy, obviously. And so that's going to be our last topic. And then this will lead us into the next classes where we're talking a lot about energy and different types of energy, different forms of energy, and energy conservation. So this is like the segue to the upcoming classes. Okay. Well, I have a confession, or at least the equations of motion have a confession. Here's the three equations of motion. You got to love these equations of motion. They helped us describe motion of objects through space and time. We found these equations of motion from the definitions, basically, of velocity and acceleration. And in fact, the top two equations are simply obtained from the definitions of velocity and the definitions of acceleration when acceleration is constant. But this equation here, this little guy that doesn't have the time in it, so that's interesting. I mean, you could say it's just, well, I've combined the top two equations to eliminate time and get a new equation of motion. But this is the equation that holds some secrets for us. And so that's what we're going to talk about, the secrets that are held by this equation. So this equation does have a secret, and that's why the Pope came to class, for the confession, I guess. Okay, so I've got to go on to the next slide. Okay, so I'm going to, on this slide, sort of, this slide is like the confession box, and I'm going to make this equation v squared equals v naught squared plus 2a times the displacement. I'm gonna make it confess. And I'm gonna make this equation confess its secrets by multiplying it by half the mass of the object that it's describing, the motion of, and by rearranging the equation a little bit. So the rearranging, if I get my pen working again here, is that I took this piece of the equation to the left-hand side, and I took these two bits of the equation, I had them on the right-hand side. And then I've multiplied by mass over 2. So look, that gets rid of the 2 here, and it gets this mass here. And it gives this half a mass here and half a mass here. And so that was a very simple exercise. It's just the equation of motion multiplied by half the mass of the moving object. But now we see the secrets of the equation. What you might spot, right? Look at this guy. Well, as you know, mass times acceleration is the net force. So this guy here is force times displacement. Force times displacement. Hold on, we've been talking about that the whole previous 65 minutes. That's the work done. We've found hidden in this equation the work done by the force. And so that's the left-hand side. On the left here, this is the net work that's done. That was hidden inside that equation of motion. On the right, we're going to find something new. This is the new thing we're finding. On the right, we find these two pieces that look like half the mass times the square of a speed. Now, one of them involves the final speed. So that's this f here. And one of them involves the initial speed. That's this I here. But they both have the same form. They're both half the mass times the square of the speed applied to the initial state of the moving object and the final state of the moving object. So some work is done over here on the moving object by external forces. And what this equation says, it changes this quantity, 1/2 times the mass times the square of the speed, by that amount that by the amount of work that is done. So this is really a huge discovery. I can't stress it enough. I can't stress how amazing I think this is. I mean, well, maybe I have overstressed it, but it is a really important discovery. That it's telling us that when you do work on an object, and forces do work on an object, the network that they do, the sort of total amount of work that they do, the sum of the works done by all the forces, that changes something about the object's motion. And what it changes is this quantity 1/2 mv squared that's associated with the object's motion. And that quantity 1/2 mv squared is so important in describing the object's motion. We give it a special name, we call it kinetic energy. And so this is our first introduction to kinetic energy, a particular form of energy, a particular brand of energy. And this relationship, this important relationship, again, is so important. It's given a special name. It's called the work-energy relation. So it connects this work that we started off by doing, by thinking about pulleys and levers and forces and displacements and machines and this notion of work. And now we've connected work done on an object or a body or a particle to a change in the motion of that particle, to a change in this quantity, the kinetic energy of that particle. And so that's actually a huge discovery for us. So let me clear that. And let me just say that, as I say, this is kind of a segue to the next classes, this connection between work and energy, where we're going to explore energy, trying to understand energy, and see the importance of energy in understanding motion and in explaining motion, and how it's a useful tool in calculating motion, in computing motion. And so we're going to focus a lot on energy in the upcoming classes.